Oh, it's working. Playing with house money right now. All right, so just to recap, since we lost about 45 seconds of recording, so convert this number. This is the 2 to the zeros place, 2 to the ones place, 2 to the twos. So this is the ones place, the twos place, the fours, the eights, the 16s, the 32s, the 64. Do our normal conversion, we get a 110 out of that. On the right-hand side of the decimal point, this is the 2 to the negative ones place, 2 to the negative 2, 2 to the negative 3, 2 to the negative 4, 2 to the negative 5, 2 to the negative 6, which is 1 over 2 to the 1, 1 over 2 to the 2, 1 over 2 to the 3, so on and so forth. That's how you do the math for that. Okay? Do all the math, you get 110.703125. Questions about that? Okay. Where did we leave off? We were going through the solution to the homework assignment. What number was the last one we did? I know we did 12. Okay, so this is where we stopped?
Yeah.
Okay, so 4D 231. Did I at least even write that?
I think you did. You started. Yeah.
Why did I put the quiz way up there?
Because you felt like it.
There we go. All right, so 4D 231 plus A4 13F. Is that right? A4 13F. Okay. So, normal math. F plus 1, that's 15 plus 1 is 16, which is what? It's a 0. Actually, let me just do a carry bit up here. Carry the 1. So we have a 0 so far for our answer. 3 plus 3 is 6, plus 1 is 7. 2 plus 1 is 3. D plus 4. That's 14 plus 4 is 18, which is that's right, D is 14, correct? A, B, C, D, 10, 11, 12, oh, 13. 13. So 13 plus 4 is 17. What's that? That's a 2. Carry the 1. A plus 4 plus 1, that's 10. Plus 4 is 14. Plus 1 is 15, which is a what? F? That's the right answer. F2370. How do you get which? Sorry. I was too busy being disappointed. I'm just teasing you.
Just how adding the hexadecimal stuff works.
Okay, so starting point is this. Starting point is learning how to click on the boxes. Let's just say we're adding decimal numbers. Actually, let me do a bigger number up here, just so we have a carry. So 7 plus 6, so we're just doing decimal math. 7 plus 6 is what? 13, which is a
3 carry the 1.
okay. So this is a 3 here and a 1 and the carry bit. So this means that we have 13. Whoa. So 13 minus 10 gives you a 3. We carry the 10. This is 1 times 10. Man, The Mac is not happy right now. 3 plus 2 is 5, plus 1 is 6. Okay, so does that math make sense? Okay, you're doing that your whole life, right? For a long time. This is the exact same thing, except we convert all the letters to their decimal equivalent. An F is a 15, an A is a 10, a D is a 13. So this very first part here, we say 15 plus 1 is a 16. It's not even my address. Okay. So 15 plus 1 is a 16. So that's a 0. Carry the 1. Doesn't make sense. Okay. Over here, same exact thing we had here. 7 plus 6 is 13. How many times does 10 go into 13? 1 time. With remainder? 3. How many times does, so this is 16. How many times does 16 go into 16? Once. There's our carry bit. With remainder? 0. So 13, 10 goes into 13 1 time. Remainder 3.
Why'd you use 16 for that?
For which one? This?
You said 16 goes into 16.
Yeah, F is a 15, right? So 15 plus 1 is a 16. Hexadecimal is base 16, not base 10. Okay, so 16 goes into 16 1 time with no remainder. 3 plus 3 is 6, plus 1 is 7. 16 goes into 7 0 times with the remainder 7. 2 plus 1 is 3. 16 goes into 3 0 times with the remainder 3. 13 plus 4 is a 17. 16 goes into 17 how many times? 1 with remainder. Actually, we did this wrong. This remainder 1. All right?
Yeah.
So 16 goes into 17 once with remainder 1. 16 times 16 is 16 times 1 is 16. 17 minus 16 is 1. That's the remainder. Then 10 plus 4 is 14. Plus 1 is 15. That gives us the F. Does it make sense now? How it works? So it's identical. You didn't have to learn how to do new math. You just had to understand how your old math worked. All right. Questions about that one? But really, that's not even uncommon. This really comes down to the whole understanding computer science. We're so good at solving problems. If I had, for today's quiz, if I had given you solve 27 plus 36, we could have all done it. But we may not have done it this way in that we actually broke it down into the individual steps. We just add them together because we know how it works. We don't know why it works. We just knew how it works. So once we break this down and understand what we're doing to add these together, then we can add these together. Okay, 14. Using BCD arithmetic, add this number. Can I copy from this? Didn't like that. Didn't we do this last time and it worked? Well, I know, but I thought once I had a... Oh, maybe it doesn't like having that... do it here. Yeah. It doesn't like having the... Hey, hold on, that's not the value I copied. Where's it getting the 7 from? All right, we're going to just do this. So that's 0, 1, 1, 1, 0, 1. 0, 0, 1, 0, 0, 1. 0, 1, 1, 0. That's our first number. Second number, 1 followed by 5 zeros, followed by 1. 11, 4 zeros, 1. All right, so these two numbers in binary coded decimal arithmetic. All right, remind me, what is binary coded decimal? What's the point of binary coded decimal?
To encode non-mathable numbers in binary.
To encode non-mathable numbers in binary. Okay, well, to encode numbers in binary in a non-mathable way. Okay, what's the advantage of that? How do we do it? So let's just say we have the number 125. What's the BCD version of 125?
0, 0, 0, 1, 0, 0, 1, 0, and 0, 1, 0, 1.
Okay, so the nibble associated with the binary number 1, the nibble associated with the binary number 2, and the nibble associated with the binary number 5. Okay, so these are broken down into fourths, correct? That's a number, that's a number, that's a number. That's a number, that's a number, that's a number. All right, so we need to do the math. Can we do BCD math? This number, well, here, let's start on this side. This number right here, 0, 1, 1, 0. What's the decimal number for that? This is the ones place, the twos place, the fours place. So this is a 6, and this is a 1. 6 plus 1 is what? Seven? So exciting, okay. This number is what? 1s, 2s, 4s, 8s, so this is 9. And this is 1, 2s, 4s, 8s, so this is 6. 9 plus 6 is? This number is 1s, 2s, 4s, 2s, this is a 6. This is the 1s, 2s, 4s, this is a 7 plus a 8. 7 plus 8 is what? All right. Well, what do we do with that? Does this mean anything? We added a bunch of nibbles together. Some of them are legal decimal digits. Other ones are not. So what can we do with this? What does it mean to do BCD math?
Carry the amount past the maximum digit.
Okay. What do you mean carry it past the maximum digit?
Like carry the amount that is past the maximum value a digit can be. So
okay.
The maximum digit can be is 9.
9. Okay. So that means we have an additional 6.
Yeah.
Okay. What do you want to do with the 6? Add it here?
Yeah, except you don't add 6. Well, I mean, you do, but it's like you're doing decimal math. It's really
Okay.
the same thing.
Like you're doing decimal math, just like we were just doing the hex math. Okay, so the 7 stays by itself, correct? Okay, now we're at 15. So what do we record here? How many times we're doing base 10, correct? How many times does 10 go into 5? Or 10 go into 15, I'm sorry. We give ourselves a remainder. So that's a 1 up there with remainder what? 5? 6 plus 7? Is that just a 7?
Yeah.
Okay, yeah, you get what I'm saying. Vision's going, nothing else is working. Steal. Okay, 15. It's a 5. And then drop down the 1 nibble. Well, that's not really what I wanted to accomplish there, but okay, now we can translate this back into BCD, which is going to be 0, 0, 0, 1. Then nibble for 5 is 0, 1, 0, 1. Nibble for 7 is what? 0, 1, 1, 1. Nibble for 5 is 0, 1, 0, 1. Nibble for 7 is 0, 1, 1, 1. So this would be our final answer. Make sense? So BCD is always decimal encoded in binary through nibbles. But otherwise, we did the same math as we did before. Whether we're adding hex, whether we're adding binary, whether we're adding decimal, whether we're adding BCD. The only thing we couldn't do is treat this BCD number as a binary number, because it's not. Okay, this BCD initial, these two values had no initial, they were it was a data representation. It didn't have a numeric representation. Okay, so we had to convert it back into its decimal equivalent to do the math. Realistically, the computer probably turned it back into decimal, then turned that decimal number into binary, then did math with the binary, then converted it back into decimal, then converted it into BCD. Or something along those lines. All right, questions about this one? All right, let's see. 15. Why is the method of shifting bits left or right to produce multiplication or division results by power of 2 preferred? Why do we prefer that? We want to multiply by 2. What do we do with it? Left shift it. We're going to divide it by 2. We right shift it. Okay? Why is that preferred over multiplying some number by 2? Let's say I take a binary number and I multiply it by 13. Forget about multiplying it by 2. We talked about how you can multiply something by 13, right? You find the biggest power of 2, then you find the next biggest power of 2, rinse, lather, repeat. So if I want to multiply something by 13, that's the same thing as adding something to itself 13 times. Correct? Well, does that seem expensive? That doesn't seem efficient, right? If I gave you a decimal problem to multiply some big number by another big number, you wouldn't just turn it into this ridiculous addition problem where you had page after page after page of this number plus itself, plus itself, plus itself, plus itself, plus itself. Boom, 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 carry the 1. You wouldn't do that, right? It's considered inefficient. So taking advantage of fast multiplication through shifts, as long as we know it only works on powers of 2, is beneficial. That way we whittle down the amount of addition we have to do to the very last little piece. So something that's going to be smaller than a power of 2 amount of addition. All right, so something along those lines would be why it's preferred, because its number of steps to do multiplication through addition is ridiculous. Okay, let's see. 16. How many positions must the number 00011011101 be shifted left in order to multiply by 8? How many? 3 times. Shift it left 3 times. Multiply it by 2, 4, 8. Make sense? All right. 17. True or false? Adding 011011101 to 101000010 in 8-bit unsigned binary will cause an overflow. All right, so let's write these guys. We have 0110. 1101. That's our first number. Second number is 101. That. All right, and the question is, adding these unsigned binary values will cause an overflow, true or false? So let's add these together. This is my carry bit. Start off at 0. 1 plus 0 is 1. 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 0 plus 0 is 0. 1 plus 1 is 0. Carry the 1. 1 plus 1 is 0. Carry the 1. 1 plus 1 is 0. Carry the 1. Just got a carry bit? True. This has a carry. Now, what does it mean for something to have a carry bit? Technically, we drop that 1 down because now we pad these 2 out with zeros. So we have a 1 in the front here, right? This is the 1's place, the 2's place, the 4's, the 8's, 16's, 32's, 64's, 128's, 256. So this is 15. 256 plus 15 is 271. So if we convert this back to decimal, this is 271. What's the range of values that could fit into an unsigned 8-bit number? Zero to 255. Okay, so you can say, yes, it has a carry bit because we had this 1 there, but that isn't always true. It just happened to be in this case because these were both represented in 8 bits. But they're really telling us that the final answer is going to be stored in an 8-bit unsigned register that can only hold values between 0 and 255. We have a value of 271. That's why the answer is true, that it does have a carry. Because the value we came up with is too big to fit in the bucket we're trying to put it in. That make sense? So make sure you understand why there's a carry there. All right. True or false? Adding 0110, 1101. Okay, same number. Same number. Okay, these are an 8-bit 2's complement binary, will cause an overflow. All right, these are 8-bit 2's complement. Well, is this first one encoded? How do you know? No 1 in the front. So the second one is encoded. How do we decode it? Take the 2's complement of it. And how do we do that? Flip all the bits. 0, 1, 0, 1, 1, 1, 0, 1. Then add 1 to that. So that's going to be that. Is that the decoded value? This is the original, and I'm going to add 1 to that. 1 plus 1 is 0, carry the 1. 1 plus 0 is 1. So these two basically just change places. So that's the decoded value. So now we're adding those two together. One plus 0 is 1. 1 plus 0 is 1. 1 plus 1 is 0. Carry the 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 1. 1 plus 1 plus 1 is 1. Carry the 1. 1 plus 0 is 1. Does that have a carry bit?
Should your
Yeah, I think
fourth from the right number be a 1 in your answer?
Fourth from the right. This one?
Yeah.
because
Yeah, yeah, it should be.
Yeah, then that's gonna change everything. 'Cause then you have to
Well, let me just start over then. One plus 0 is 1. 1 plus 0 is 1. 1 plus 1 is 0. Carry the 1. Oh, that's where I messed up. 1 plus 1 is 1. Carry the 1. 1 plus 1 is 0. Carry the 1. 1 plus 1 is 0. Carry the 1. 1 plus 1 is 1. Carry the 1. 1 plus 0 is 1. That? Now a question. Does that have a carry bit? Oh, it fits. Okay. So that will not cause an overflow. It will fit in the destination. Fit inside of an 8-bit number. Another way you could have done that, I suppose, to get that same answer, is you could have converted both of these to decimal. So this guy, this first one, this is the 1s, 2s, 4s, 8s, 16s, 32s, 64. So this is 96, 104, 108, 109. And this is the 1s, 2s, 4s, 8s, 16s, 32s, 64. 64 plus 16 is 80, 88, 92, 94. So this is negative 94. Because this was a 2's complement, right? Then 109 plus Negative 94 is 15. Will 15 fit inside 8 bits? Doesn't even tell us if it was signed or unsigned. Well, signed by definition because it's 2's complement. So negative 127 to positive 128? No, other way. Negative 128 to positive 127. Fits, right? So that works as well. Ultimately, the question we're asking is, will the final result fit in the container that we have built to hold it? Okay. And finally, number 19, what would be the best binary representation for each of the following applications? So these are all values, and we need to represent them in binary. So consider that we're trying to solve the job of a computer. That is, computer likes to store all of its information in binary somehow. All right, that's the whole reason why we've had BCD and converting between hex and binary and all that crap. So we're storing a phone number. What's the best binary representation for a phone number? Well, how many digits are in a phone number? Depends whether you keep the area code on there. Depends whether you have the international, the extra one, or the whatever the code is. Okay, so what would your recommendation be for the binary representation of a phone number? And why? I guess I didn't specifically ask you to say why, but we'll talk about the why. Go ahead.
Probably a
10-bit number? Okay. Let's think about a phone number. So a phone number all right, so that's my phone number. We can leave the dashes out, and we'll assume there's not an international code, right? So, excuse me. So if we're going to treat this as a gigantic number, a 10-bit number, now let me ask you this. We'll give you the benefit of the doubt here. You want it to be an unsigned 10-bit number because we don't need to have negative numbers for phone numbers, right? Okay, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's the biggest number we can represent with a 10-bit number. This is the ones place, the twos place, the fours, the eights, the 16s, 2s, 4s, 8s, 16s, 32s, 64s, 128s, 256, 512. This is 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128 plus 256 plus 512. That's 1023 is the biggest number we can store in 10 bits. Is that less than 123? A lot bigger than 123. So 10-bit number is not going to cut it.
YouTube, you just put your phone number out there.
So my phone number's on my syllabus and all the other stuff.
No, but now more people can access that.
You can get like propositions from people.
I have a question about binary coded decimal. It's like, wait a minute, I'm on the final box of Upper Black Rock Spire. And I'm in Bible study. I just described the last hour and a half of my life. Literally. All right. So, Jared, do you understand why a 10-bit number won't work there? We can't, each of the bits, I get where you were going with it. You were saying, okay, well, there's 10 digits here, right? So we have 10 individual digits. Great. So we can represent each of those as a bit. The problem is that each digit in decimal has to be able to hold between 0 and 9. What's the smallest binary number, smallest number of bits to represent a 9? Ones, twos, fours, so 4 plus 2 is 6, plus 1 is 7, so a 3-bit number can only hold a 7. 4 bits? Okay, so really we need 4 bits per digit. Isn't there 10 digits? Right? So 40. Or we should start adding in international codes and stuff. So 40 total bits. So you can make that argument. Now, so would you just store this math value as a 40-bit number? You could. That would be a valid answer to this question. Especially since, I'll have to call him back. Especially since it doesn't ask you to give explanation. I wish it did, but it didn't. So we could certainly do it as a 40-bit number. Do you have a better
BCD.
BCD? Why BCD? Still, it would still be a 40-bit number, right?
Yeah.
Still be going to be 40 bits, but why would BCD be preferred?
Doesn't need to be mathable.
Yeah, two reasons. One, we don't need to do math. Doesn't need to be mathable. We just need to store that value in binary. And number two, quicker conversion. Right? We can convert it to that and convert it from that much more easily than convert this gigantic value. Which, what is this value? 2.6 billion. So we don't need to convert 2.6 billion to binary. We can just do the BCD on a per nibble basis. That makes sense? All because this core value that we're trying to represent, doesn't need to be used for math. All right, questions on that one? All right, age as a positive integer. It's interesting how they specified positive here, but I guess they just assume I was going to say, it seems like they just assumed we knew that a phone number would be positive, but they didn't assume that we knew age would be positive. So, how would we represent an age as a positive integer? Who? I hear like mumbling and I'm maybe a grunt. 4-bit unsigned? Okay, right off the bat we could just say unsigned. Because we don't need to worry about negative ages. Oh, here, this one's for you, Fritz. Who was the oldest guy in the Bible? Technically, we might need to expand this a little bit to support older folk, right? So one thing you have to consider here is the lifespan of a human being, right? The Bible, who was the oldest? Was it Noah? No, Methuselah.
Methuselah at 900 something.
Okay, so to be biblically sound here, which gets me a Christian worldview point, definitely. So I can mark that. Biblically sound. We need to be able to store. Let's go 1,000. How much? How old was he?
I mean, it doesn't exceed 1,000.
Okay.
969.
969. Okay, 969. So that's the largest age we need to be able to hold, given the biblically oldest person ever recorded. Okay, so how are we going to store that? It's going to be unsigned. So realistically, for our world, we could probably say maybe the biggest number we need to store is 150. It's probably safe. Yeah, for now. Yeah, until we start doing Terminator hearts and stuff, which I'm banking on that. It's funny, like I look at today's world, and you see all these people that go and do all the plastic surgery and stuff like that. And, I like, what's the point? It's like idiots. I'm going to be first person in line for elective Terminator surgery. Give me the DNA reading eye and. Like, wouldn't that be awesome? I don't even want him to cover it up. I want to look like a cyborg.
The Apple Eye, the eye.
Yeah, eye, right, exactly. Man, that would be awesome if I could be like one of the beta testers. So I didn't have to pay the ridiculous money for it, because it's going to be expensive. First person who gets a Terminator leg. I mean, they have prosthetics and stuff now, but not a full functioning Terminator leg. Plus, that comes with time travel, I think. it's what's up? What'd you say?
I could be wrong.
I'm pretty sure that's part of the premium package.
Is that time travel forward or backwards?
That's true. Could they couldn't go back, could they?
Would you-
No, they did go back. They were from the future, so they went back, but they couldn't go forward.
Do you
If they went forward, they would just go till after the war was done and just continue on.
Do you want to go back?
Yeah, I think that'd be really interesting.
Just get all the Terminator surgery and then go backwards?
Yeah. I like where you're going with this, especially coming from the no technology guy. Brought to you by Amish Technologies. Become a Terminator today. We've mapped the entire human genome using corn. Oh, all right. So age, you could make an argument for probably like a 7-bit number, something like that. 7-bit would let us do 128 plus 64. You could probably even do less than that. 64-bit number. I'm sorry, 64-bit. A 6-bit number. That would let us do 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. That would probably cut it. So something like that. Your argument should be something based on how old do we need to be able to represent. Give us a big enough number for that. All right. But for Methuselah, we're going to need a larger number. So we already decided that 10 bits won't cut it, right?
No, that was
Just over 1,000, so a 10-bit number. So your answer was right, but for this one. It's for Methuselah, because age can be represented as a 10-bit number. All right, exam grade. Typically, we think of these as percentages. So we need to be able to store a maximum of 100. Maybe decide there's some wiggle room for extra credit, but no big deal in this case because we can't really store just 100, right? So, well, it depends if it's single or double precision. Java double precision would be a, what is it, let's say, 48 bits on the right. I think it's 64 bits total. Oh, I get what you're getting at. Maybe your exam grade isn't a whole number. Maybe it's a percentage. Or like, you've got a 62.3894662, repeating, of course. Now, the funny thing is when I said repeating, of course, how many people got the reference I was trying to make? The 2 World of Warcraft players. Most of you have heard of Leroy Jenkins, right?
32.3%
Yeah.
chance of survival.
If you go way back to the original Leroy Jenkins video from World of Warcraft when they're in, it was Upper, right? Upper Blackrock Spire. This guy runs into the room and hatches all these eggs and just wipes the whole group. But they're sitting there like debating what the chance of survival is and stuff like that. And so one of the guys on the video is like, he's supposed to be the crazy mathematician, and it's like, I've calculated a chance of success of 33 point blah blah blah, repeating, of course. So, what was I talking about? Oh. Right. So you certainly could make an argument to represent it as a larger value. Double precision might be rough. But certainly a single precision floating point value, which would be the smallest floating point value you could support by the IEEE standard, to allow for percentages in between whole numbers, you can make that argument. I don't think that's unfair. But my guess is most of us kind of gravitated towards the integer, the whole number. Do any of your teachers give you percentages in on a paper? I understand at the end you might have some decimal places, but like if you get a test back from a teacher, or you get a paperback. I mean, does anybody give you like an 87.25? Huh?
Never on like the paper, so.
I mean, yeah, when your grade is mathematically calculated by Angel, your average might go out to a couple of decimal places, but on an individual grade, that wouldn't happen, right? That would be funny. How do you decide to take off 3/4 of a point?
It happened in nursing.
It happened in nursing? Really? You lost 3/4? Well, first of all, why were you in a nursing class?
Well, before.
Okay. So you were in a nursing and you dropped because of that. Because that's nitpicking. It's like, I took off 0.2 points of a 0.2. I took off 0.2 of a point because because of the.
You didn't capitalize word.
Yeah, I mean that's like the type of thing I could do for like I guess light handwriting from State Farm. Hey, man, I didn't think that existed. So I guess you are right. If we're gonna be all inclusive here, we're gonna have to do the jump from what do we need? How many bits do we need total to get up to 110? So 64s, 32s, 16s, 8s, 4s, 2s, 1s, 7-bit number-ish. 7-bit number would probably cut it. So rather than a 7-bit number, which would cover us at the integer level, you want to be memory inefficient. And we'll go with a 32-bit number, just because we don't need as many decimal places. We're going to the lesser of two evils. But it's not wrong. It's absolutely true. And apparently for nursing, it's required. So well, then again, when it comes to medical stuff, you definitely want to be precise. I don't want my doctor rounding up or, for God's sake, rounding down.
Somebody rounded up. That's why you got only knew you had one kidney.
Well, I got a new good medical story for my. Yeah, this one's good.
Is the shaman again?
No, this is from the new endocrinologist they sent me to. I don't know why I find it funny because it could be bad. There's nothing I can do about it now. I mean, I'm banking on the whole guy has a good sense of humor thing, so I'm set. I'm fine. So I went to his new endocrinologist yesterday for the thyroid issues. My other doctor had put me on this testosterone replacement stuff. New doctor wants to pull me off of that because some of the symptoms, like with just the tremors in one arm or something, she's like, I want to make sure it's not a pituitary tumor. It's like, okay, have a good day. Maybe that would explain the vision thing. I'm going to get that Terminator head before we're done.
We're just gonna come in one day for classes.
It's like, oh my gosh, is this like an Iron Man thing? Yeah, but I did this myself. This is the carburetor from a dune buggy. That's right.
It's like Jerry, it's like duct tape to your side.
No, seriously, that's the kind of stuff I would do.
With a screwdriver and some
Yeah.
spray foam.
Well, yeah, I told you that with the air conditioning install at my previous home in Illinois. I had to get the air conditioning in this little small window. The smallest air conditioner I can get didn't quite fit, so I could carve up. It was down in the basement. I had to carve up a bunch of the foundation. I just did that with a hammer and a screwdriver to get through like the metal and stuff they had there. And then I just decided to utilize that kind of sort of bent screwdriver as part of the structure. Because when you pulled the air conditioning thing, you know how it has like the accordion thing on either side to keep it open like in a window? Well, this wasn't like a normal window. So to keep one of the accordion things open, I put the screwdriver in there and then spray foamed all around the expanding foam. It was in. Just saying.
So you see what you're saying is you look a little surprised for whoever asked for a
Guy I sold the house to. I also left him with a 65-inch rear CRT, rear projection CRT TV in the basement.
That'll be there because I know it's destroyed.
Yeah, one of the really giant ones, not the flat panels. That's why it sold with the house. And when Best Buy came to deliver that, they were supposed to take it to where it should end up, and I wanted it in the basement. They refused to take it down there because they said it won't make the turn. I tried to argue with them and said I did the math. They refused to take it down there, so I got one of my students over, and we decided to get it down there. Somewhere there's a video of that too. And this is one of those staircases where it goes down, then turns, then comes back on itself. So after it slid down the first flight of stairs and through the wall, it didn't go all the way through the wall, but it went part of the way through the wall. Then we had a little more wiggle room to turn it because we had a broken wall.
Should have just told the guys at Best Buy, no, we can make enough room.
That's right. And then when we started turning it, the wood thing on the step, we had to rip that off. I never put that back up. That was because the wood was like a custom cut piece of wood that we snapped in half. Yeah, so that's sold with the house. Very good. Professional install. Even with my house right now, I have a old style Pepsi machine in my basement. When Awesome Fat first started, the original Fat Cave was in my basement. So we had office space and stuff down there. So we got this, for like the cool Google effect. We had this big, we went on to Craigslist or something like that and found this Pepsi machine. But back from the old days where they weighted it down with lead. So like you walk up to this Pepsi machine and you try to like push it, it will not budge. It weighs like 2,000 pounds. It weighs so heavy. So it took like 8 of us to get this thing down the stairs. There's a video of that somewhere too. And this one doesn't turn back on itself, but my stairs go down, then at an angle, then down, then a 90-degree turn, and then but it's kind of a short landing. That was a lot of weight with gravity helping.
Good thing that one didn't slide down the stairs.
No, but if I could find that video somewhere, it's entertaining. We had at least 8 or 9 people. Somebody could have died. Easily.
Well, the hot tub with full,
Yeah, the hot tub was fit. We had what, 15?
No, I was talking more so just the drive behind it.
Oh, that was funny. That was funny. All I'm saying is I have a long history of endangering students.
No, we should go to Speed Queen for violence.
That's right. Speed Queen for dinner after dark. That's right. That would be actually an interesting test to do. Like you could either take the final exam or opt out of the final exam, but you have to go to Speed Queen with me after 8 p.m. and eat in there. I wonder if the workers would just like warn you. No, you have to leave.
Drive my car.
It's like a policy after the sun sets, one must provide their own bulletproof vest in order to eat in the restaurant.
Hey,
They got some pretty good barbecue. It's pretty worth it.
We just gotta drive my car.
Why?
Because
No one can steal his car.
Yeah, nobody. You can leave the door unlocked.
Nobody's going to steal a car that says Awesome Fat all over it. What are you supposed to hide that? I mean, they might steal the tires or something, but anything with a logo on it. All right. So, exam grade. Checking account balance.
Negative trillions for the U.S.
So you're saying it needs to be a signed number. All right.
Very large.
So you would like it to be a signed number, okay? Does it need to have decimal point value?
Yes.
Probably. So it needs to be, at the very least, a signed single precision value, which will let us get up to some giant number, but not necessarily infinity. So maybe we even say it should be a double precision value for bigger bank accounts or bigger deficits, as it may. And more importantly, does it need to be mathable?
Yes.
It does. So we really couldn't store this as a sine BCD doesn't really exist-ish, but there's no reason why we couldn't represent a signed number in BCD with an extra nibble out front. we wouldn't have to, but since we do want this to be mathable, it wouldn't be an option. Go ahead.
This has nothing to do with this, but because it's time sensitive. Evan wants to know, because the reason he's not here is something about making friends with our bathroom. And he wants to know if you want proof.
Yes. Tell him to send it quickly. Class is almost over.
He needs to sing.
And we need to have show and tell. All right, let's finish this real quick. So checking count balance, double, single precision, floating point number, reasonable enough. You could have probably also made an argument that it should be always a positive balance. Wouldn't have been an unreasonable argument. So figure out what's the biggest amount of money that would go in there. But anyway you cut it, it's got to support decimal places. Value read from a postal scale. Okay. Got to support decimal. We decide at what level of precision. So at least a single precision, if not a double precision, if you need to weigh it out to something crazy. Typically, what does the postal scale go by? Tenths of a pound, something like that. Something like that. So that kind of concept. Price.
Did you get it?
I did. So price, same thing. It's got to be a decimal value. Probably going to be a positive number. So that type of thing. Let's see where we got here. Okay. Anyways, I'll look at it here in a second. Any questions about any of that? So that was the whole homework assignment. I should have the grades up for it by Thursday, definitely. I'm pretty caught up on my grades now. On Thursday, we're going to start talking about logic gates and we're going to actually write software to represent each of our logic gates so we can utilize our own software to create programmatic gates. It's going to be kind of interesting. There's a couple of tools out there we might look at as well. All right, I'll see everybody on Thursday.